So, when you put all these things together, what is going to come? Integral gz dz. G is continuous, and so it is bounded in a neighborhood. Some call the bound M. What is left over? Dz. What is dz? Epsilon I e to the power it. When epsilon goes to 0, it will go to 0, right. That is what it says. Integral gz dz up over gamma epsilon, right. Integral gz dz upon gamma epsilon will go to 0 as epsilon goes to 0, simply by parametrizing. So, in our example, the rho is 1, the signed angle is minus pi, and so limit of f of z dz as epsilon goes to 0 is minus I pi, correct. Integral of fz dz upon gamma epsilon, epsilon goes to 0 is I pi, minus I pi. Is it clear? Then what is left over? In the double star equation, what are the things? In the double star equation, what are the things? That integral over gamma z, gamma epsilon was there, which we have just finished calculating. What is left over? Integral over gamma r, that will go to 0. That discussion is going to be postponed. So, if you take that equation double star, which you have written down, and let epsilon goes to 0 and let r go to infinity, what do you get? What do you get? Integral of minus infinity to infinity sin x upon x dx minus pi equal to 0. Remember, imaginary part has been taken, and we got minus I pi, but I will go away, imaginary part is being taken. So, integral of sin x upon x dx from minus infinity to infinity is pi. Is it clear? It is called the fractional residue theorem. Suppose P is a simple pole of F and gamma epsilon is a circular arc of radius epsilon centered at P. Then subtending an angle alpha at P. Alpha is measured in radians. So, integral of as epsilon tends to 0, integral fz dz gamma epsilon is I alpha, where alpha is a signed angle measured in radians, which is positive if gamma epsilon is traced counterclockwise and negative if gamma epsilon is traced clockwise. This is called the fractional residue theorem, and we are also proved the fractional residue theorem. How do you do it? F of z is, let rho be the residue. How does f of z look? F of z is rho by z minus p plus gz. So, integral fz dz over gamma epsilon is integral of rho dz upon z minus p plus integral of gz dz upon gamma epsilon. Integral of gz dz will go to 0 because g is analytic, so it is continuous, and so you are left with dz. Dz is epsilon I e to the power I t dt, and epsilon is going to 0. So, gz dz will go to 0. What is left over? Rho dz upon z minus p over the arc. And how do you calculate this integral? Actually calculate it. Put z equal to p plus epsilon e to the power I t and finish it off, right. So, exercise, prove the fractional residue theorem. Write down the steps clearly. Next exercise, prove that sin x is greater than or equal to 2 by pi x. This inequality is called the Jordan's inequality. Jordan's inequality is sin x greater than or equal to 2 upon pi x. The picture explains to you very clearly how the proof goes. Sin x is a concave function, right. Second derivative is minus sin x. So, it is a concave function. So, the graph is going to lie above or below? Above the chord. The chord is very clearly written, shown in the picture. The graph of y equal to sin x is going to lie above the chord. Look at the graph between 0 and pi by 2. This is your point pi by 2. This is a point pi by 2, and at pi by 2 look at this chord. This chord is going to be below the arc y equal to sin x, correct. The chord joining 2 points will lie below the graph between these 2 points. And so, you find the slope of this chord, the slope of the chord turns out to be 2 over pi x. So, the equation of this line is y equal to 2 over pi x. The equation of the graph is y equal to sin x, and the graph of the sine function lies above the graph of the straight line. In other words, sin x is greater than or equal to 2 over pi x. That is Jordan's inequality. Sin x is greater than or equal to 2 over pi x. Use this inequality to show that limit as r tends to 0, r tends to infinity, 0 to pi by 2 e to the power minus r sin t dt is 0. And then show that in the previous example, limit as r tends to infinity, integral f z dz over gamma r is 0. Please do these exercises, all right, and finish the problem. Next exercise, compute integral minus infinity to infinity cos pi x upon 2 dx upon 1 minus x squared, and the next exercise is integral sin pi x dx upon x into 1 minus x squared. Use semicircular contours with indentation. For this one, which is the function we will take? F z equal to e to the power I pi z by 2 upon 1 minus z squared. Where are the poles? Where are the poles of this? Plus or minus 1. So, you have to make how many indentations? You have to make an indentation at minus 1 and you have to make an indentation at plus 1. 2 indentations have to be made, because there are 2 places on the real axis where the function has a pole. For here, how many indentations you have to make? 3 indentations. Next problem, by integrating e to the power 3 I z minus 3 e to the power I z plus 2 upon z cube along a semicircle indented at the origin, calculate minus infinity to infinity sin cube x upon x cube dx. So, your function that I am giving you the function now, and I am still giving you the semicircular contour. What is sin cube x? Sin cube x is, how do you write sin cube x? Use the formula sin 3x is 3 sin x minus 4 sin cube x. And that is how this comes, that is where this comes from. But then why is this plus 2 here? What are the plus 2 doing there? I think this should be enough, right? E to the power 3 I z minus 3 e to the power I z. That should suffice. Why is the plus 2? You could put in a 4 if you wish. That 4 sin cube z, no? 4 sin cube z is sin 3 z minus 3 sin z. So, you can put in a 4, does not matter. Question, and I would like you to seriously think about this question. Why is it that f z equal to 1 over 4 z cube into 3 e to the power I z minus e to the power 3 a z is not suitable for the purpose? Why should I add that plus 2? Remember the previous question? The plus 2 is given here in the function. Why is that? I would like you to give it a thought. Next question, by integrating e to the power minus z squared along a sector with opening angle pi by 4, prove that integral 0 to infinity cos x squared dx equal to integral 0 to infinity sin x squared dx equal to root pi by 2 root 2. By integrating e to the power minus z squared along a sector with opening angle pi by 4 and using Jordan's inequality, prove that integral 0 to infinity cos x squared dx equal to integral 0 to infinity sin x squared dx equal to root pi by 2 root 2. These are the Fresnel equation, Fresnel integrals. Fresnel's integrals, they appear in the theory of Fresnel diffraction in physics. Prove that integral 0 to infinity e to the power minus x squared sin x squared dx equal to 1/4 root pi square root of root 2 minus 1. I am not giving you the function and I am not giving you the contour anymore. Next is evaluate integral sin x dx upon sinh x from minus infinity to infinity using a rectangular contour of height pi indented at I pi. Take f of x equal to sin z upon sinh z. Whenever hyperbolic functions come, typically you will use a rectangular contour. When you see a hyperbolic function in the denominator, you will use a rectangular contour because the hyperbolic function has several zeros, no? Sinh z is 0 at 0, I pi to 2 pi I. So, if I take a semicircular contour, large number of them will be inside and will be stuck. So, use a rectangular contour typically when you see hyperbolic functions in the denominator. Calculate the Fourier transform. Calculate the Fourier transform of e to the power minus x squared. We have done this in MA 108 also by using differential equations, but here I want you to do it by using complex analysis. Calculate integral e to the power minus infinity to infinity e to the power minus x squared cos x psi dx, where psi is bigger than 0, by integrating e to the power minus z squared. I am being very kind to you, I am still giving you the contour and the function. By integrating e to the power minus z squared along a rectangle of height psi by 2, along a rectangle of height psi by 2. Hint, calculate e to the power minus x squared into e to the power minus ix psi. The sine integral will be 0. The sine integral will be 0, odd function. The cosine integral is non-zero. So, here I am still giving you the function and the contour. Prove that integral minus infinity to infinity e to the power ax dx upon e to the power x plus 1 equal to sine by pi by sine pi a. Prove that integral minus infinity to infinity e to the power ax dx upon e to the power x plus 1 is pi by sine a pi. What does this pi by sine a pi remind you of? The beta gamma function. Gamma a into gamma 1 minus a. So, use a rectangular contour of height 2 pi. Right. So, this finishes end of lecture 8. End of lecture 8 and we stop here.